Well, welcome back, everyone. We're almost there. Hello. And it's official. Welcome back. It's almost the weekend, so happy almost weekend, folks. We're nearly through week 5, and pretty much once we get through section 3.3, we're just collecting more and more rules for differentiation. We'll have an application section we're going to be looking into in chapter 3 on exponential growth and decay as well. But the big applications we're going to see as far as differentiation goes are all going to be contained in chapter 4 pretty much. After we complete chapter 4, the course switches over to the next big topic, integration, which in a certain sense is the inverse of the differentiation problem, but it has a surprising actual problem that we're solving, finding the area under a function. But for as far as the announcements go today, we're pretty much just getting started with section 3.3. We're on example number 1. What we did was introduce the differentiation rules, the derivative of a constant like square root 3 being 0, the power rule. If we differentiate x to a power, the power moves down and the new exponent is 1 less. We combine that with the sum and difference rule and the constant multiple rule to differentiate polynomials like these. In fact, we can differentiate any polynomial whatsoever in just this kind of fashion. We go term by term by term, that's here's a constant, so it went to 0, to get these results. Then the exponential function is the tricky one. The derivative of e to the x is just itself. 10 was multiplying, so constant multiple rule also took effect here. That's why it's just multiplying in this spot. And e, that's just a constant. There's no x by it. It's not e to the power of x. So it vanished in differentiation. And it's easy to kind of lose our way, sort of, once we're in the weeds of all these differentiation rules. We need to always remember that the derivative is this, the limit of a difference quotient. I'll only ask you to do exactly one problem like this one where the limit comes up on an exam 2 setting, possibly once on the final exam as well. But aside from that, we're always going to be using these properties here to differentiate. Well, any questions at all, folks, with the wrap up of where we left off so far? Okay, before we get into 3.3, there's an excellent question asked to be brought to class. So thanks to the student who asked about that. One of the problems that's really tricky to think about, sure, the derivative is that. Sure, we can compute them pretty quickly, but if I give you just a random graph, how would you plot the derivative? That's an extremely tricky question. We did 2 of them in the notes, but you really have to practice a lot of them to get a feel for it. The homework in WebAssign has several problems of practice there. And so to start us off today, let's refresh on how this goes. What I did is I stole a problem for WebAssign. I felt like this is a really good one for us to take a look into just to see how it goes. And we're going to connect the dots between this idea here and solving the problem below. Yeah, so the differentiation rules are line by line in the 3.3 notes going down from the very top before we get to the example 1. So yeah, some people have encountered this one. One thing I found really tricky about this problem was it gave the derivatives first and then the function second. I just switched it over for me. So I have it giving the function first and the derivatives below. So here's the major idea that's going to make all this work happen for us. The derivative, no matter how abstract it gets, whether we're looking at the limit definition or we're looking at the differentiation rules we see in the 3.3 notes, it's that limit, but it's literally just the slope of the tangent line to the original graph y equals f of x at a given point x. So let's give this a try. You're going to need to get as much vertical space as possible. This one's kind of hard to fit on one page. Let's maybe go to 120% zoom. So the instructions are to match each of the 4 different functions. Here are the y equals f of x functions on the top. With each of the 4 different derivatives, I through IV, 1 through 4, I guess is an easier way to say that. So here are the derivatives down below. Now it's really hard to get that zoom just right. Are people able to see this okay so far? Okay, so I have functions here, derivatives below, these are pretty tricky. So let's think about them. And while we're looking at these, considering them, just think in your mind, the derivative, the graph below, is a graph of slopes at any point x. So actually the one you probably want to start off with is the weirdest one on the set. This one is kind of like a zigzag pattern, or maybe zag-zig pattern, however we think about it. It's interesting because if we're here, that's a linear function. And the slope here, whatever it is, it's a positive quantity, but it's the same positive slope wherever we are on this branch right here. And suddenly it hits a peak and it switches. Now the slope is a negative quantity, and it's that same constant value, negative quantity, until we make a sudden switch again to a positive value. Anyone see which of the graphs below? Let me see if I can make this just a little bit easier to read. This is A, B. Oh, hang on. No, that's not right. That's kind of hard to see. This is A, B, C, and D. And this is graph I. There we go. Double I, 3, and 4. Okay, so anyone see which graph B matches a derivative below from 1 through 4? Yeah. Yeah, absolutely. This is the right graph. So we can say, let's see, how would we answer this? I'll just say B corresponds to I. So if this is our function y equals f of x, we have a positive derivative here that corresponds to this positive value, and it's the same all the way through here. And that's why it's the same through here as well. Then it becomes negative. That just means if the slope is negative, the curve is below the x-axis, and that's what we see down below here. Curve stays below the x-axis in that entire range to correspond from here to here. In that entire domain is a better way to say it. Then it flips to positive once we're on this branch. So that point might correspond to this point over here. So the odd one out is actually probably the easiest one to match up when you're thinking in terms of slopes altogether. And let me see if I can write my answer down in a slightly better way. I'll put the answers just up here so we can see B matches with I. In other words, this is the graph for the derivative of the function over here in part B. Now, it's a lot of matching problems, but the further we go, the easier it gets, right? Because this becomes elimination in a certain sense. I would say, in my opinion, the next easiest one is the one with the most turning points. Because a turning point is where the graph goes from where it's increasing to suddenly decreasing. So that's one turning point. Decreasing to increasing is 2 turning points. And then increasing to decreasing is 3 turning points. But the reason these turning points are really important to us is, if we scroll up for just a moment, the derivative is equal to the slope of the tangent line. So in practice, when we hit a local maximum or a turning point, we have a horizontal tangent line, which means slope is 0 at this point, at this point, and just again at this point. So if we're trying to match that up, it's not going to match up with 3, right? Because this has 2 0 values, so 2 turning points altogether. It can't possibly work out. But if we look at part D with maybe graph 4, that actually works out. We have a point here to match the first time we had a horizontal tangent line. Second time we had a horizontal tangent line matches up here, right on the origin. And then finally, up here, we have our next turning point. Hang on, let me try again. Got a little mixed up. The turning point is where it's going to connect on the x-axis for a 0-valued slope. So we have those 3 values, but just because it intersects 3 times doesn't guarantee the graph is right. Here's the next thought. We want to think in terms of increasing and decreasing. the curve is increasing in this range, that means the graph has to be above the x-axis for the derivative. So that's what we see here, above the x-axis. So the thought is here from this graph, if f is increasing, then its derivative, f prime, is positive or just above the x-axis. So we're increasing all the way up to this range until we get to a horizontal tangent line, zero slope. That means the derivative, y equals f prime, down here, is above the x-axis because it was increasing. Then it hits zero to correspond to the horizontal tangent line. And same thought with this, but in the opposite direction. If f is decreasing, so let's match up those colors a little better. If f is decreasing, say going down on the curve, that means we can say if f is decreasing, I'll use DEC for decreasing, I ran out of space, then f prime is negative. So check out in this range, we're going down, and the derivative in this range is negative. It's below the x-axis. So far so good. This is all tracking the way we expect it to. Increasing here means we better be above the x-axis. And we are. We stay above until we get to here. That spot where the horizontal tangent line occurs, the turning point, where we change from increasing to now decreasing again, means the curve is going down. So now we can say with a lot of confidence and clarity that the graph D matches with its derivative graph 4. Does that make sense to folks, matching D up to 4? Awesome. There's just two graphs left, sorry, to match up. We have graph A, graph C. This one's kind of tricky with one turning point and looks like a horizontal asymptote we're approaching here and here. This one's tricky too, but it has two turning points, so it might be a little bit easier to see which one goes to which. But I'll leave it up to the class. Let's take a look at the last two candidates that we have on. It's graphs 2 and 3 to match with graphs A and C. Any volunteers for one matching pair? Let's take a look as we think about it. A and 2. Let's see. I don't think A and 2 go together, actually. The trouble with A and 2 is this one has a turning point here. So here's where we would have a horizontal tangent line, slope m is 0. And we have another turning point here. So we would have a horizontal tangent line, m is 0 on this one. So we would expect 2 points of intersection, one on the negative end of the x-axis and one on the positive end of the x-axis. Again, these are pretty tricky kind of problems when you think about it, doing this kind of matching. It turns out the one that matches with this information is 3. We have a 0 value here for the derivative, a 0 value here for the derivative. That's not the full story. Let's think in terms of increasing and decreasing. It starts by decreasing first, so we need to be below the x-axis. So that matches up. Then it starts to increase thereafter. So we have to be above the x-axis in the range where the original function was increasing. From here, we are indeed above the x-axis until we hit the second turning point. Then it's decreasing in this range. So that's the below the x-axis part right here. So it turns out that it looks like graph A matches, and keep that color the same. Graph A matches with graph 3. But if that's really true, we need to make heads or tails of how does graph C match with graph 2, the last one on paper. We might think that's plausible because it's by elimination now, right? But let's see if we can really reason through how these two connect. If this is really a y equals f of x above, is this one, graph 2, really f prime at x? So that's the question that's left on the paper so far. Before we address this last connection, any questions at the moment coming up with any of these? Okay, let's actually do one additional thing. There's two kinds of challenges here, really. This is a matching problem. So the challenge is navigate all of this dense and busy information to find which graph we're going for. But a whole different kind of challenge is to do this. Take just one graph, as we're about to, and from that one graph, plot its derivative by hand on your own from scratch. That's harder in my opinion. So let's justify what we said in the last page by sketching the graph of this derivative. So we'll call this y equals f of x. We want its derivative, y equals f prime of x. But this is the mantra that helps us think about the geometric connection and how we plot this. No matter how you think about this, the limit of the difference quotient as h goes to 0 or the differentiation formulas, this is always the slope of the tangent line to y equals f of x at the point x f of x. So if we can really make heads or tails of that, we'll have a graph down below, and then we'll peek above to see if it's plausible, what we drew versus what was in that multiple choice kind of matching problem. Okay, so let's sketch down below the derivative in green. Here's y equals f prime of x. And first, the turning points are really where it kind of dissects where the graph is above and below the x-axis for the derivative. So I always go for these local minimums or local maximums, or said differently, where it turns from decreasing to increasing and vice versa. Right through here, we get the horizontal tangent line. That means m is 0, but then we make this connection. If m is 0 there, at a value of x is 0, this means f prime at 0 is 0. I put an input value of 0 because that's where we were on the graph when we put in that point of tangency, 0 itself. The output is 0, so we go to the graph of the derivative, and we have 1 point down. That's the only turning point we have, but from there we can get started. Say, for example, you put down a point anywhere. Maybe it's here. Put a tangent line on that. Tangent line might look, let me see if I can make it look a little bit more plausible and believable. Tangent line might look about like that at that point. But what I can say for sure about that slope is it's negative. We're not trying to calculate it exactly. This is just a qualitative freehand sketch, not an exact diagram of the derivative. But if I have a negative slope here, notice it stays negative the whole time until we get to the horizontal tangent line. It's always negative. But out here, sure, it's negative, but the horizontal tangent lines get really, really flat here. So if I put a tangent line in this region, m is approximately 0. It's pretty close to 0. Maybe it's hitting it exactly. And same over here, approximately 0 in this region. M, approximately 0 in that spot as well. That's telling us something about the graph. I don't have other turning points, but I know regions where the curve is becoming so horizontal, say around here, the tangent line slope is going to be very close to zero. So I'll put a point here to match up with that approximate zero. I'll put another point here to match up with the approximate zero. You could probably put them pretty close to the x-axis. This is a little bit exaggerated just to get a good visual. And then here's what happens next. It's decreasing faster and faster and faster as we move right to left until we get closer and closer to the turning point. But if it's decreasing, that means the whole curve should look like this, decreasing faster and faster and faster until it gets closer and closer to the turning point. So that's my sketch so far. Here it's doing the opposite thing. It's increasing faster and faster and faster. That's probably the maximum value of increase around here. It's still increasing, but leveling off until it gets close to the asymptote. So it goes about like this. It's approximately zero, but you know what? I think this curve should be slightly better. That point would have been above. This is pretty tricky. This one is meant to be negative close to zero. This one's supposed to be positive but close to zero because it's always increasing here. And that just kind of shows how tricky these kind of graphs can be. But here it goes. It's increasing faster and faster until somewhere in the middle it's starting to level off and drops lower and lower. And that's about what the curve would look like. If I go from just a hard dot here to a hard dot here, that would be my approximate graph. Any questions at all, folks, producing that graph there? Okay, let's see how we did. So back up here, we said graph C matches with graph 2. And yeah, theirs is way better, well, a lot better. It shows a lot of more interesting qualitative features. But if we were doing a by hand sketch, and this is what you gave me, that does the job. Doesn't have to be perfect. It tells us about what the derivative should look like. Well, that's the wild landscape of really looking into this concept that the derivative is nothing but a slope at any point x. Any questions at all, folks, revisiting that topic on plotting these functions? Okay, thanks again for the student for asking that question. And just a pretty big call out to anyone in the class. At any time we're about to start class, I always just call out any questions before we get started. And that's a completely open-ended invitation. Don't hesitate to throw anything out there. If you have something you worked on WebAssign that you want us to visit at the start of class, you can email me, and that's a great way to engage. But once we run out of questions, we just go back to the material. So here's where we left off. At the end of Tuesday's class. So we did this problem before. We did this exact problem. That makes this one kind of an exciting problem. We want the full equation of the tangent line to this curve at the point of tangency 1, 2. Now, the reason we're revisiting this exact problem is because we have brand new tools available to us. Let's go back down memory lane, not that long ago, but kind of feels like a while ago. This is how it all went down. We had only this as a tool. We were connecting limits and continuity with the new definition, the derivative. We didn't even say this was the derivative yet, but we now know the slope at the point of tangency is the derivative. We had to carefully expand f at 1 plus h into this quantity. Then we found the slope was -2 finally, after taking the limit and plugging things in very, very carefully. Then we used the standard equation building. We were going with this strategy, the point slope form. We threw in the slope and we got down to the tangent line. And we knew it was a tangent line because when we plot the function against that tangent line, this is what it looks like. The more we zoomed in, the more the original curve and the purple tangent line looked like they were completely the same. So let's revisit how we're going to do this now. If you see this problem, say on exam 2, and this is the whole set of instructions, you're not being asked to use the limit definition. I would do this to start. Step 1, if this is your y function, you can now just write either y prime or you can write dy dx, either notation you prefer. We're going to use the differentiation rules. Power rule first happens here at y equals on the x cubed part. Power rule says 3 comes down as a coefficient. The new power on x is 2. Then we do it again. If it's x power 1, all we get is -5. And we have 2 justifications for that. That's both the power rule. That's also a linear function of slope -5. So the derivative of that term is -5. Then finally, that's a constant. Its derivative is 0. And we have the entire derivative. You might have also called that f prime of x if you wrote y equals f of x. And even if you didn't, if you called this f prime of x, I'm going to assume you are thinking in these terms. Y is the f of x function. So that's our step 1, just compute the derivative. Step 2, we go back to the topic we were just looking at. The derivative, no matter what you call it, a y prime, an f prime, or a dy dx, it's the slope to the tangent line of the original function at any point x. But we're most concerned about the point at 1. So we can write y prime at 1. Here we're kind of forcing in function notation with y. If we're using Leibniz notation, we could call this dy dx. Evaluate at the value x equals 1. And you don't have to write all 3 notations. We're just kind of doing a notation roundup to say the ways you can write this, the ways you'll see it in the book and other problems. Or you could just call it at f prime at 1. Either way you call this, again, you don't have to write down all 3. All you're really doing is plugging the 1 right here inside your derivative. So you get 3 times 1 squared minus 5. That's going to be a 3 minus 5 for a value, -2. Let's really connect the dots on that. The derivative is the slope of the tangent line, so let's call it m to really make that connection. This is, in fact, exactly what we did. If I can get this to behave, there we go. This is exactly what we did with all these interesting steps we see above here. We did the limit. We got all the way down to a slope of -2 after a lot of algebra. The limit doesn't look too bad on paper here, but that's because this is a cloud of algebra that was kind of hidden to get to the part in blue right here to run through the limit. And notice how fast we got there. Using our differentiation rules, we just get the slope picked up practically right away. So that's the value of all these interesting tools we have. Computation now goes a lot faster. Step 3, we're just finishing it off. So I would go y minus y1, my highlight kind of went away there, equals the slope m times x minus x1. We already have the slope m, and we were provided with the y1, x1 values. They're right up here. So now we have y minus 2 equals slope m for -2 times x minus 1. So now we can finish this off. Y minus 2 is -2x plus 2. And so y equals -2x plus 4. And that's where the whole problem ends. Let's just peek really quick to see if we really got that. Yeah, here it is, -2x plus 4 to match up with our work exactly. So that's kind of nice in a way, right? This was like a 10, 15-minute problem when we carefully worked out all the algebra. This one you could probably do in 5 minutes. We talked our way through it, so it might have taken a little bit more than 5 minutes. But now we have some amazing tools to get the same kind of results. All the derivative provided was -2. So if you want the equation of the tangent line, that's everything else we produced. So that's where step 3 gets involved. Well, any questions or comments at all, folks, with the rundown on example 1? Okay. Other things we can do is take higher order derivatives. So if I have a random, this looks like a polynomial function here with an interesting constant, root 18. We want to make heads or tails of what is f triple prime of -1. And there's a kind of a nice analogy to this. If, say, f of x represents velocity, say for a object that's falling, something that's thrown upwards on the planet Mars, like we looked into in section 3.1. Or hang on, I got this backwards. Well, not backwards, wrong starting position. Sorry for folks in pen. If f of x is the position function, so the height of an object at time x, then it probably works better with a t here. So again, sorry with everyone working on pen today. Let's go with a t because usually we're thinking in terms of time. So if this is f describes the position, say height of a function at time t, f prime at t is the velocity. How fast it's moving upwards or moving downwards. The second derivative, f double prime, is going to be the acceleration. How fast the rate of change of the velocity is changing. We have a constant acceleration due to gravity, about -9.8 meters per second squared near the surface of Earth. And it's the same kind of thing here when we say acceleration. And we're going one order higher, f triple prime. F triple prime at t, this is defined as the jerk function, and then we start to lose names beyond there. The jerk function is going to tell us how fast is acceleration changing. Fortunately for us being humans on the surface of the Earth, the jerk function is 0. Acceleration is a constant, -9.8 meters per second squared. Yeah, in a certain sense. And in fact, it will be doing an inverse in the sense that some problems later on in the course, we might have acceleration and we'll go backwards to velocity, backwards to position function. That's when we're going to be using integration tools to make that happen. But yeah, that's a great analogy to think about this. So the jerk function is kind of interesting. If you're, say, building a roller coaster and you're analyzing just the vertical position of the person on the ride at any time t, you want to have acceleration be exciting, or else it's going to be a boring ride. But you want to make sure the jerk function is well controlled, or else you don't want people flying off the rails. If that's a big value, then acceleration is going to be insane. Velocity is probably going to be lethal and all sorts of things going on. So that's what triple prime might represent as a physical quantity in this problem. But when it comes to doing this, if you want to get to the third order derivative, you just differentiate it line by line, derivative by derivative. Start with f prime at x. Here we begin with the power rule, or comes down as a coefficient. We multiply it by x cubed. Then we just go term by term. This is the sum and difference rule. Now it's a power rule and the constant multiple rule. 3 moves down, it just multiplies the -4. So this becomes a -12. New power on x is 2. Then we just keep going down the line in that kind of way. Some difference rule, now power rule, and the constant multiple rule. The end effect is just that we get plus, take 2 times 19, so 38. New power on x is a 1. When we go to differentiate this one, same process, except the new power on x is going to be 0, so x vanishes. And we get just a 3 on this one. Plus 3. And because this is a constant, it just completely vanishes. It goes to 0 in the derivative. So let's just say here, for emphasis, constant. Derivative 0. And if you put plus 0 here, no harm, but we would often just leave it off. We still have more work to do. We want to go to the third order derivative. That means we're thinking if with us was the position function for some roller coaster, we found the velocity function at any time t. I already put variables x, but we could switch it to t. On the second order derivative, we're looking into the acceleration. But it's just really the same kind of process. Polynomials are kind of nice in this sense. In fact, the higher derivative we take, the easier it gets because terms are disappearing on this thing, right? We did a high enough derivative, it's just going to be zero and it's going to stay zero at higher and higher order derivatives if it's a bona fide polynomial like this one. So let's go down the line. Using our rules together, it's 4 by 3 for a 12. New power on x is just a 2. Rinse and repeat, multiply, keep the sign. 2 by negative 12 for a minus 24. New power on x is 1, so we just write that one as a x. And now it's linear, so we keep the slope 38. The plus 3 is a constant, and so it's a plus 0, we just leave it in this form. Does that look all right to folks so far, to this line? Okay, let's keep on going. Third order derivative. You know, it gets kind of tedious writing down prime, prime, prime. What if it was the 10th order derivative? That would be kind of a nuisance to write down. So it's nice to know there's a shorthand here. The third order derivative at x can be expressed in this way. And those parentheses are vital. If you take off the parentheses, it means f composed with f composed with f 3 times. The parentheses are our way of saying, no, not function composition, we mean differentiation 3 times. But no harm just writing out this way either. I'll leave it up to you how you prefer to write it. You could call this f parentheses 2, but more often you'd see f double prime in this kind of way. But no matter how we notate it, we're doing the same exact thing. Differentiation rules take over. It's 2 times 12, so this is now 24. X has power 1 less, so just x. Now it's linear here, so we just keep the slope, negative 24. Last term is a constant, so it's gone. And we're just about there. What we wanted was the output at negative 1 to the third order derivative. And here it is. We can say dot, dot, dot for a fancy way of saying therefore. Third order derivative evaluated at the constant negative 1 is, put a negative 1 there. That's 24 times negative 1 minus 24. So negative 48 altogether. Well, that's the rundown of this kind of problem. It's kind of a tricky one because we want to calculate f triple prime at negative 1 right away, but you have to jump through these 2, 3 different hoops before you even get there. Then you can actually go to the original question, input the constant to get the value out. Well, any questions at all, folks? Okay, so the fact that we got to negative 48 tells us this function is pretty erratic if we were to look at its graph. Let's take a look at it just for the sake of the fun of it. It's f of x equals x power 4 minus 4x cubed plus 3x minus square root 18. So I've got the function in now. Naomi says, will we not have to plug it into the other equation like we did before? Not in this question, because this question was more just calculate an output and didn't just stop at that spot. The only time you would have to take this step 3 like we did on the prior problem is specifically if it says find the equation of the tangent line. This is pretty much the one and only time we would do that additional step. Here, we're pretty much on our problem we just did, was we got the value for the derivative, except it happened to be a third order derivative on this one. Other questions at the moment? Yeah. Oh, thanks for spotting that. On Desmos, I forgot that term right there. Good eye, thank you. So plus 19x squared. Okay, so there's our function. And we were investigating what's going on at negative 1. So we are not quite negative 1 here. But you'll notice that as I try to get to negative 1, it is an enormously steep curve. It's going up so fast, it's hard for me to get a good plot without changing the scale on this axis. So the fact that we had a non-zero value here was telling us something. There's some rapid change on the original function around -1. A lot of other values, but that's pretty much the process of getting the higher order derivatives, the big takeaway on this one. What we're going to do next is we'll practice more with all of our differentiation rules we've seen so far, but now look into a context of what does this look like in an applied setting? This one's kind of basic, nothing too major going on. Our most interesting applied problems are going to be in chapter 4 on optimization, but example 3 down below is going to get us started. Here's how it goes. Notice the notation is not our favorite. There's no y equals f of x here. We have L and A, but this is par for the course in any kind of applied setting. We have to pick the variables that match up with the context we're working in to make the model feel more meaningful. So we're being told biologists have proposed a cubic polynomial model. That's why we see degree 3 for the cubic, to model the length L of an Alaskan rockfish at age A. So this is telling us the roles of those variables. We have a length, and it's a cubic polynomial taking the cube of age, square of age, and age itself in this interesting combination, plus the constant 1.21, to model the length of that fish in inches at A years old for the Alaskan rockfish. I don't know very much about Alaskan rockfish, so when you see a problem like this out in the wild, say on Web of Science, not a bad idea to just go here, Alaskan rockfish. Thinking about the problem in your subconscious, it's a good idea to just get a feel for what you're even looking at. These are crazy looking fish. This is my first time Googling this. It's a good idea to just get a feel for what you're looking at. These are pretty big but vibrantly colored fish. We're just trying to model the length from nose to fin, I'm assuming. So those are the fish, pretty interesting. Wonder if they're tasty now. Haley says, don't see capital. Yeah, that's right on this one. The model is involving capital letters, making this look kind of funny as well. I agree with that. Instructions say, calculate DADL evaluated at A is 12, include units that give a practical interpretation of your answer using the context. So again, this is a very common exam question. For exam 2, something like this on the final exam, the derivative would be half the credit, and the interpretation would be the other half of the credit on something like this. This one works in stages. So let's say for a step 1, let's compute the derivative. It's being indicated in Leibniz notation, and that is pretty common for applied problems like this one. But if you wanted to, you could take DL, DA, and just call it L prime. That's just a change in notation. Well, I wouldn't say it's harmless. Best practice is to keep Leibniz notation because that helps with the units. If you prefer to see it this way as a shorthand, that's okay. So for step 1, let's do DL. This is the rate of change of the length. DA means with respect to the input variable, A, the age of the fish. But now that we're there, we're not doing anything too fancy. This is just the power rule. Power A comes down, multiplies the 0.0155. We're going to need a calculator here. So take 0.0155 times 3, 0.0456. And we now have A to the power 2. So we're just using our differentiation formulas just like before. This power 2 is going to multiply that coefficient. Power drops to 1. So wrong tab, sorry about that. We're going to get negative 0.372 times 2, double checking the numbers, for negative 0.744 A. That number 2 looks funny for some reason. Let me see if I can fix that. Finally, on this term, it's the linear term, A power 1. A always vanishes when we're here. We just pick up the coefficient plus 0.395. excuse me, 3.95. I'm saying my numbers with the wrong place value. Last, it's a constant, so this part goes to 0. And we're done with step 1. We have the derivative of the length of the rockfish with respect to its age in years. But that's not exactly what we wanted. We wanted to evaluate it. We don't want the tangent line equation, we just want the slope essentially. And the slope has a special meaning in this problem. We'll say what that meaning is as we go to the practical interpretation, but so far this is step 2. Take dl dA. This little funky bar that you see right here is just saying evaluated at. We are evaluating our derivative at A is 12. So that's just a fancy way to say plug in 12 into these numbers we see here and here. If we do that, we're going to get 0.456 12 squared plus, rather, minus 0.744 times 12 plus 3.95. So there are our values plugged in. Back to the calculator on this one. So oh, hang on. I'm getting my decimals kind of mixed up here. Let me fix that copy error first. 0.0456. Now let me check the rest of the numbers there. 0.456, 12 squared minus 7.744, 12 plus 3.95. So we get this figure 1.5884. Definitely struggling with my decimal points on this. Does that look accurate to folks so far? While I double check these numbers. Okay, well, we got it, folks. We've computed DLDA evaluated at A is 12. That's 1.5884. But we want the units on this. And this is the beauty of Leibniz notation. Leibniz notation is telling you the units. It pops out on page. You look at the numerator units was in inches. So we have, let me drop this down just so we can see this better. We have 1.5884 inches. Then with this, you can just write a fraction bar if you prefer. You can say per, completely up to you. The denominator is telling us our other unit in per year. So these always match up. The numerator units divided by the denominator units tells us that number is 1.5884 inches per year. So final thing we need to do is just put this all together. We have to include the context. So I'll make a big deal out of it when we say the context at any point using that color pen and saying what that figure right there represents. But any questions at all? Just getting to the number with the units itself? Okay, to wrap this one up, here's what we can say. Let me just scroll down for a bit. When the Alaskan rockfish is 12 years old, now the sign here matters because it's positive. We'll say is growing. And I imagine it's going to be growing over its life cycle. But if we're looking at some other context where something is shrinking for whatever reason that might be, and we see a negative sign, we would have to say shrinking as opposed to growing. But because there's truly a positive sign here, I'll put positive lightly since we don't normally put a positive sign on a positive number. We'll say the fish is growing at the rate of 1.5884 inches per year. So specifically at that age of 12 years. Haley says, could you use something like this for half-life? Let me think about that. So half-life, we're talking about something shrinking every, say, time unit, we have just half of it. And yeah, absolutely. We're going to look into half-life equations along the lines of, say, y equals some constant, maybe e to the negative, say, 3 times t. And when we go to calculate dy dt, we'll have units of, say, maybe this is measured in grams per, and maybe if t is measured in time, maybe years, year. But because this is half-life, we would say shrinking. Because our derivative would be, that's starting to get a little bit scrunched in there. Let me see if I can put that together better. Units, grams per year, perhaps. Well, we'll say in this case, shrinking. And we, in fact, will look into those kind of problems. That's going to be one of the applied sections that we're going to take a look into in section 3.6. So yeah, this absolutely carries over to half-life type problems as well. And this one's a half-life problem only because of the negative there, making it an exponential decay problem, which comes equipped with a bona fide half-life as well. Other questions at the moment? Okay, well, this is the whole rundown of doing a problem like this one. Yep, you bet. Thanks for asking about that. When this one is being graded in an exam situation, it is pretty tricky. When we say mention the context, we can't just say the number is increasing by this many inches per year. We have to mention what are we talking about? What is the thing that's growing, shrinking, whether it's a population, a person, an organism, and so on. We have to say whether it's growing or shrinking. We got a positive number, so we said growing on this. It could be something moving up, positive derivative, versus moving down, negative derivative. And we need to bring in the unit as well to hit the context to say exactly what's going on. And the number one easiest mistake to make when we do this is to accidentally say when the rockfish is 12 years old, it's 1.5884 inches long. But that's not true. This is, at 12 years old, a pretty big fish. I mean, I think I got rid of that screenshot. There it is. It's a big fish. At 12 years old, it's not anywhere near 1.5 inches. It's just growing at that rate, 1.5884 inches per year. So the number one mistake that's easy to make is, let's put it down here on paper. The derivative is a rate. Is the big idea. So you'll always see something per some other unit. It's not, say, the population size. It's not the length of the fish. It's how the population changes per year or how the fish grows per year. But we have to capture that some way, somehow, when we give the interpretation. But we spend a lot of time on this problem because it's both fast to kind of get through, but it's very, very tricky. The variables are different. L and A, capital variables. The thing had units so that we had to bring into the problem. That made us really look at Leibniz notation. And we'll practice doing step 3 on more and more problems as they come up, interpreting the derivative as we see it, because this is like the most important thing in a real sense, right? What is the value of the derivative, 1.5884, if we cannot say exactly what it means in context? That's the major skill we have to take away. But from beyond this point in the notes, we're just going to practice ordinary derivatives without context. So let's give that a try on the next page. I gave a big hint, and this hint carries over to the problems you're going to see in WebAssign. This is always a great hint. Look before you leap. Some of the problems can be a lot harder than you might expect. But if you do some algebra, simplify it a little bit first, they go quite a bit faster. Let's look at these one at a time and practice these as we go. First, we have a ordinary polynomial. This one's kind of nice. It does have something funky going on, that e power 4. Now, e power 4 is a constant. It just looks really abstract when you put it on paper. And we can convince ourselves of that by going e power 4. There it is. It's always 59.598 and some change, no matter what. So watch out for e power x is not constant. And if you had an e power of x in the problem, you would say y prime is itself e power of x. But this one's easy to miss because we're often thinking in terms of this differentiation formula here. If the x is missing, it just doesn't work whatsoever. So now let's do the derivative on this one. I'll just call it using Newton's prime notation and ordinary y prime. And first thing that happens is we multiply here to here. We'll get a negative 24 x power 3. So that's one term down, and we just go down the line in that kind of way. Here we multiply this way. 3 times 2 is going to give us a plus 6. Power goes down by 1, so now it's x power 1 in the derivative. That term is done. And so is that term. It's a constant, so nothing happens to it. The derivative of e power 4 is 0. So that's our first one down. Some of the problems in the homework is really just that. So if you see a long list of problems in the 3.3 WebAssign homework, it's because some of them are actually just really fast problems like this one. Any question at all, folks, getting through that first one here? Okay, some of them look built up, like say, this one looks like there's just a lot going on out of nowhere. So here we're going to take our time with this, working it out algebraically. There is a way to differentiate a function times a function times a function, but this derivative is not the derivative of the square root times the derivative of 4x minus 3 times the derivative of x minus 3. It's a totally different derivative. We're going to see how that works in the next section, 3.4, the product and quotient rule. But this one doesn't actually require the product and quotient rule. If we saw this on the next section, we would still just use the same tools we have here. We would expand what we see. So let's do some algebra on this. F of x is going to be equal to, first thing we do is use the exponent law. So I'll write out these laws as they come up on the margin to the right. Square root of x, we've seen this one before, can be re-expressed as x power 1/2. So I'll put x power 1/2 here. Next thing we're going to do is just FOIL out 4x minus 3 times x minus 3. So ordinary algebra here, multiplying that way, we get a 4x squared. Here to here is minus 12x. Here to here is minus 3x. And here to here is plus 9. This is still not in a good form to differentiate. I mean, 2 reasons. If you can combine like terms, less work on the derivative. But the major reason is a multiplication here. We don't have a rule for that yet. We have a constant multiple rule, but that's no constant whatsoever. So we need to go further on the algebra. F of x is, I'll leave x power 1/2 here, simplify inside, 4x squared. But you know, as we simplify, let's make our exponents compatible with that exponent. X power 2 is just as good as x to the power 4/2. So now we have the same denominator, 1/2. We have negative 15x here, but we can call that x power 1 also to power 2/2 plus 9. So next is a distributive law, and the exponent law we need is a power of n times a power of m is a to the power of n plus m. And it doesn't matter if they're fractions or even worse, irrational numbers, that power rule works just as normal. So for an example, on the right, if we took x power 1/2 times x power 4/2, this becomes x to the power of 5 halves altogether, because all we've done in effect is take 1/2 plus 4 halves to get that 5 halves. So this distribution is tricky at first. We have to use those exponent laws carefully with fractional exponents. We're going to get 4 x power 5 halves to start. Then when we distribute from here to here, we get minus 15. It's 1/2 plus 2 halves, so x to the power 3 halves altogether. And last one is not the worst. Go here to here, and we just get plus 9 times x to the power 1/2. So finally, we are there. We took careful care to expand this. So what we are represented with, it's not a polynomial like before because we don't have integer coefficients. But it works just like this problem. All we're going to now use is the good old power rule that goes like this. The derivative with respect to x of x power of n, and n can be any real number whatsoever. It will always be n times x power n minus 1. So we're going to use that for our brand new exponents. They're a little bit less nice, but it still qualifies in the power rule. I would say the algebra is probably the trickiest part, though. Any questions at all, folks, getting to that level, that step there? Okay, here is finally our derivative f prime at x. Using the same exact process we've taken before, we multiply here to here. I'm going to do this in stages and write it as 4 times 5 halves so we can see the change. Then the new power on x is 1 less. But 1 less in this context just means take 5 halves, subtract 2 over 2. That's going to give us 3 halves. So in other words, all I've done to get this is take 5 halves minus 1, which is 5 halves minus 2 over 2, to get the 3 halves down here. And rinse and repeat. We multiply here, so it's negative 15, times 3 halves, x to the power of, take 3 halves minus 1, that's just 3 halves minus 2 over 2. We're back to power 1/2. And so what happened to this exponent is we took 3 halves minus 1. And we keep on going. Now on the next one, 1/2 times 9. So here's 9 times that 1/2. The new power on x is 1 less. Suddenly that feels a little bit more tricky. This can be a negative value when we use a power rule. Nothing's going to stop that from happening. This is 1/2 minus 2 halves, so we get a new power of negative 1/2 altogether. So going here to here, that was 1/2 minus 1, which is really 1/2 minus 2 halves, giving us that negative 1/2 as an end result. So the major thing that was annoying about this problem was it was factored. We had to unpack that. Factored is sometimes nice for simplifying, but not for this formula, which goes term by term with nothing factored whatsoever to use all of our rules. Then we had to use fractional exponents, so we had to carefully navigate how these work out, subtracting the ones. And we're still not done. We have to simplify all of this, so let's simplify to the final step. F prime of x, 2 goes into there, so we're going to get 20 divided by 2, so 10. X to the power 3 halves. No simplification here. This is just negative 45 halves, x to the power of 1/2. Same on this one, plus 9 halves. X to the power, negative 1/2. And this would be a perfectly reasonable spot to end your work on this. You could take more algebraic steps to express this as, say, the square root of x cubed and then reduce that square root because it would reduce. It would involve potentially an absolute value. It gets kind of convoluted. You could rewrite this one as a square root. You can drop this one to a denominator with the square root, but I'm going to consider that always optional and completely up to you. Here is exactly where the calculus ends, and so this is always a very acceptable stopping point, including on WebAssign. This is an answer that you can put in. It's completely acceptable. So let's put here, just for the sake of notes, this is an acceptable stopping point. Well, that's a tough derivative for sure. We spent a little bit more time on getting through this one. Any questions at all? Finalizing part B? Okay, they're not all meant to be a nasty algebraic slog like this one, but there's a couple in WebAssign that go like this. So I felt like we just had to put it in the notes as well. Some problems in WebAssign are really fast, like this one. This one is just another redo of exponent laws. If you have 1 over a base a to a negative exponent, you can promote that up into the numerator with a positive exponent. And that's vital because our power rule right here by the red dot relies on the base, whether it's x or t, that base needs to be in the numerator for this rule to flow exactly as written. So the very first thing I would do on this one is just re-express it as 9 t to the power positive 2/5. Then we're pretty much there. You could call this y prime. Let's use Leibniz on this. You could also call this dy dt. Then the power rule says 2/5 comes down, multiplies the 9. So 9 times 2/5. And let's see what the exponent should turn into on this one. Let me think about that. Yeah, absolutely. As a decimal, negative 0.6. I was thinking, it took me a moment to compute. I was thinking 2/5 minus 1, right? So that would be 2/5 minus 5/5. So we would get negative 3/5. And let's go with your value. Negative 0.6 is perfectly acceptable as an exponent. So let's go negative 0.6. My first thought was negative 3/5, but they are exactly equal, so no harm done. Watch out if it was, say, an exponent that comes out along these lines, however. Say it was 5/3 in a different problem. Now we have an issue. We can't put this without having the exact format, so this would be the easier way to say it. Well, all the questions so far? It's not done. So if that was your question, that'd be a good question. Last thing we still have to do is simplify it all the way down to 18/5 t to the power negative 0.6. And that would be the answer on that one. Well, this is pretty much, again, the overall review of all of our differentiation formulas so far. Last two questions are pretty tricky. The part A was the more standard version of the problems we'll see. And when we look at part D, this one's kind of weird. A could mention area of something. S might be the side length of some geometric object. These get tricky because we're used to seeing X's and Y's. So if we mix up the variables, suddenly it feels like a tougher problem. But really, this one is just a little bit more practice, just like before. I would say part E is going to be the tricky one. So let's see where we land after doing part D and make a decision if we want to do this one. I wouldn't want to rush through part E. And by the way, with where we're at so far, looks like we will need another day to finish off this unit or this section completely. So I'm going to move the due date on Canvas and on WebAssign as well. And you can start this section right away if you want to get early start, but you might run into some problems like these that we just haven't done quite yet. Let's give this one a try next. The idea is we're pretty much just doing what we did in part C 3 different times. We also have to do a little bit of exponent surgery on that thing. So let's make this one the big thing we focus on to start out. 1 over The fifth root of S cubed is not in any way, shape, or form in a convenient form factor if we're going to use the power rule for the derivatives. So we start by going like this. This is also S to the power 3 divided by the index that you see in the root. So we're kind of going, say, this is on paper somewhere. Sorry for scrolling up. We're kind of using this rule here, but going backwards. So we went from the root, or actually we're going forwards. It's the same rule, but different index we're using. If there's already a power 3, we just take 3 divided by that index, the fifth root. Then next step we take is we need the base to be into the numerator. So we go S now. The trick here is to make it not look like the number 5. S now is to the power -3/5. We change from denominator to numerator, we flip the sign. Same rule as what we saw here, but just a different version. That's 1 over a to positive n. That can be a to the negative n. But the big takeaway is switch positions. You're switching the sign of the exponent. So that's going to fix what we have going on here. And the rest of them are just uses of this exponent law repeatedly. So here's our new function, better format. A of S is really -3, S power -4, plus 9, S to the power -3, and seeing the work on the right, this is plus S to the power -3/5. And once we get here, we're pretty much done. You could call this dA, ds, Leibniz notation like we did above. But I want to emphasize prime notation is just fine as well. If you call it a prime, I'm good with that. Let's go with prime notation. Let's pause on the moment and think about this one. If that's your first term there, any volunteers for what the derivative of that first term should be? What number or what algebraic expression would you put down here? Yeah, absolutely. Thanks for writing that in, Ashlyn. It's exactly positive 12, good call, S power to -5. It's tricky because the exponent is always going down, and sometimes it's easy to get mixed up on the direction. We're always subtracting -1 literally from whatever we see, so now it's down to -5. So exactly as you said, this term becomes positive 12, S power -5. It was negative times negative, the old exponent -4 times coefficient -3, and down 1 brings us here. Now, rinse and repeat. This will be -3 times 9, so -27. The new power is 1 less, so it's S power -4. Yeah, exactly. Good call, Haley. The chat came in right as I was penning that in. Awesome. Then this is kind of like the tricky one, right? But no matter how bad your exponent gets, same exact process. Any volunteers for what will happen on this very last one? This is one of those ones where it's also kind of hard to format in chat as well, if you're typing it out in chat. This will be negative, I think you're on the right track. It would be a -3/5, and I would have written this in as a -8/5 altogether. So let me check the calculator. -8/5 is indeed the -1.6. So yeah, absolutely what you have there. So this would come in as, I'm going to bring down the -3/5 as a coefficient now. S is going to have power 1 less. So if you wrote it in as a fraction, subtract 5 over 5 and you get -8/5. But I want to make an additional comment that this is just as good equivalently. I'll absolutely accept this answer. -3/5 s to the power of -1.6 does the job as well. Let me double check my numbers there. I keep clicking on the wrong thing. So if you wrote it this way with a decimal number, that would be great. Well, we did it, folks. This is most of the problems you're going to see in the notes. I have a couple weird ones we're going to take a look into to finish off the notes, but we're just about there. Sorry for running just a bit over the minute. But any last questions, folks, before we call it a night? Okay, well, have a great weekend, folks. Thanks for your hard work and participation today. And we'll be back to these notes, finishing it off when we're back Tuesday. I'll extend the due date as well on WebAssign. But have a good one, folks. And have a great President's Day. I forget we're going across a holiday too before we come back. Take care.